The sea has always been a place of both wonder and war, a silent theater where technology meets survival. And here, cutting across the horizon, is a ship that represents the pinnacle of both. The USS Gerald R. Ford, America's $13 billion floating fortress and the most advanced aircraft carrier ever built. It's not just a ship, it's a self-contained city, with its own nuclear power plant, medical facilities, security teams, and a full aviation base capable of launching and recovering dozens of aircraft. Everything a modern city needs to function is compressed into a single moving platform of steel, stretching 1,092 feet long, spanning 256 feet wide, and rising approximately 250 feet from keel to mast. It covers nearly 4.5 acres of sovereign U.S. territory that can sail anywhere on Earth's oceans. And this is just the beginning. Stay with us to the end to uncover the engineering, power systems, crew life, and flight deck innovations that make this the world's most advanced carrier. Don't forget to subscribe to Corecraft Engineering to catch every engineering marvel we explore. For decades, the backbone of American naval power rested on the Nimitz class, nuclear-powered giants that ruled the seas since the mid-1970s. Each ship carried twin reactors that gave them virtually unlimited range and sustained operations across the globe. But by the early 2000s, their design had reached its limits. They required over 5,000 crew members, costly midlife refueling, and relied on steam catapults, massive piston-driven launch systems that use pressurized steam to hurl 30-ton aircraft into the sky in just seconds. Maintenance grew expensive, efficiency lagged, and technology outpaced the design. So in 2005, the Navy made a decision, not to improve what existed, but to start over. The result was the Gerald R. Ford class, a carrier built from the keel up to define the next half-century of naval engineering. Thousands of engineers, technicians, and shipbuilders spent nearly a decade constructing the USS Gerald R. Ford at Newport News Shipbuilding in Virginia. At full load, the USS Gerald R. Ford displaces nearly 100,000 long tons of seawater, built from high-strength naval steel forming over 2,000 compartments and 25 decks, linked by millions of feet of electrical and fiber optic cabling carrying power and data to every system, from reactors to radar arrays. It introduced 23 major new technologies, including EMALS, electromagnetic aircraft launch system, AAG, advanced arresting gear, A1B nuclear reactors, producing 3 times the electrical power of the Nimitz class, a redesigned island for improved flight deck visibility and aircraft handling. The Gerald R. Ford isn't just modernization. It's a complete re-engineering of the American supercarrier, built to define naval aviation for the 21st century. At the core of the Gerald R. Ford are 2 A1B nuclear reactors. Together, they generate 3 times the electrical power of the Nimitz class, enough to sustain a small city. They drive 4 massive shafts, each spinning a 30-ton bronze propeller, pushing this giant at 30-plus knots, 56 kilometers per hour. That power also runs every onboard system: radar, catapults, water purification, and entire living quarters. This energy surplus prepares the Ford for the future. Railguns, laser weapons, and directed energy systems already have the power base they'll need. The defining feature of any aircraft carrier is its flight deck, a 4.5-acre platform of reinforced steel engineered to operate as an ocean airbase. At any given moment, dozens of aircraft can be positioned on the 4.5-acre flight deck, while the full air wing carries up to 75 aircraft, a mix of F/A-18E/F Super Hornets, F-35C Lightning IIs, EA-18G Growlers, and E-2D Hawkeyes. The Ford can launch and recover aircraft 25% faster than older carriers. At full tempo, the carrier can sustain around 160 sorties per day, surging to over 270 during combat operations. Every launch and recovery is a choreographed operation involving hundreds of crew members, precision timing, and real-time coordination with advanced flight systems. Aircraft are launched using EMALS, the electromagnetic aircraft launch system. For decades, carriers relied on steam catapults, massive piston-driven systems that converted superheated steam into linear force. They were effective but maintenance-intensive, imprecise, and stressful on aircraft structures. EMALS replaces steam with linear induction motors, electromagnetic coils embedded beneath the deck. As electric current flows sequentially through these coils, a moving magnetic field propels a shuttle forward, accelerating aircraft from 0 to approximately 150 knots, approximately 280 kilometers per hour, in 2 seconds. This system provides smooth, controlled acceleration, reducing airframe stress, compatibility with a wider range of aircraft, including future drones, reduced maintenance requirements, greater energy efficiency, powered directly by the ship's twin A-1B nuclear reactors, more precise control over launch energy, about 30% improvement compared to steam. Launching is only half of flight operations. Every takeoff must end with a precise landing, a moment where a 25-ton jet slams down at 240 kilometers per hour and must stop in less than 100 meters. Traditionally, carriers used hydraulic arresting gear, massive fluid-filled pistons that absorbed the aircraft's energy when it caught one of the deck's arresting wires. Effective, but difficult to maintain and often too rigid for lighter aircraft. The Ford introduces the Advanced Arresting Gear AAG. Instead of hydraulic resistance, it uses electromagnetic energy absorbers combined with digital controls. When an aircraft's tailhook catches a cable, sensors calculate the jet's mass and speed in real time, adjusting magnetic resistance to bring it to a gentle, precise stop. This system not only makes landings safer, but also allows a wider range of aircraft, from heavy fighters to lightweight drones, to recover on the same deck. Real-time digital control constantly monitors and adjusts deceleration, smoothing the stop, reducing stress on both aircraft and deck, lowering maintenance needs, and enabling faster turnaround between landings, all fully compatible with next-generation UAVs, unmanned aerial vehicles, or drones. The flight deck operates with exacting precision under extreme conditions. Crew roles are identified by uniform color: yellow shirts, aircraft directors; position and guide planes for launch and recovery; red shirts, ordnance handlers, manage weapons loading and safety; purple shirts, fuel handlers, oversee refueling operations; green shirts, catapult and arresting gear crews, operate and maintain EMALS and AAG systems, ensuring precise aircraft launch and recovery; white shirts, safety officers, monitor deck operations and enforce protocols. Beneath the flight deck lies the Ford's massive hangar bay, carefully divided into 3 zones by fire-resistant bulkheads. 1. Maintenance zone, where aircraft are repaired and mechanically prepped. 2. Ordnance, armament zone, where weapons and bombs are stored and prepared for loading. 3. Refueling, servicing zone, where jets are fueled and readied for flight. These divisions ensure that if an accident occurs in one area, it won't immediately affect the others, keeping both the crew and the aircraft safer. High-tech electromagnetic elevators, replacing traditional hydraulic lifts, transport planes between hangar and flight deck in seconds, drastically increasing turnaround rates during operations. This is where the air wing breathes, rests, and prepares to strike again, forming the nerve center of the carrier's combat capability. With over 4,500 crew members, the Gerald R. Ford operates like a self-contained city, where every human is part of the ship's engineering ecosystem. Life aboard is intensely structured. Sailors live in berthing compartments shared by 3 to 4 personnel, with minimal privacy. Every space is optimized for efficiency. Bunks fold, storage is stacked, and pathways are narrow, designed to maximize room for machinery, cables, and systems. Operations run on 12-hour shifts, maintaining continuous power, propulsion, radar, catapults, and weapons systems. The endless hum of the reactors and turbines is a constant signal that the ship is fully alive, and every system depends on human supervision to function flawlessly. Meal preparation, over 18,000 servings a day, is orchestrated by around 120 skilled culinary specialists working in coordinated shifts. The operation is timed and automated to sustain crew performance during relentless flight operations. Recreation areas and gyms exist not for leisure, but to maintain physical readiness, essential for safety and rapid response in emergencies. The Gerald R. Ford operates with 700 fewer crew than the Nimitz class, not because it needs fewer sailors, but because it has advanced automation at its core. It has smart sensors that constantly monitor propulsion systems, reactor output, fuel flow, and power distribution, detecting anomalies before they become critical. Robotic maintenance arms, touchscreen control panels, and integrated diagnostics allow the crew to focus on precision operations rather than repetitive manual checks. The Gerald R. Ford is designed with layered defensive systems to protect the ship, crew, and mission-critical functions. Its architecture combines kinetic weapons, electronic warfare, and structural redundancies to survive missile, aircraft, and sensor threats. Close-range defense comes from the Phalanx CIWS, a 20mm Gatling gun capable of firing 4,500 rounds per minute. It is guided by radar and computer algorithms that predict incoming missile trajectories, allowing near-instant reaction times to destroy threats before impact. For medium-range interception, the ship relies on RIM-162 ESSM missiles, integrated with advanced radar tracking. These missiles can engage multiple targets simultaneously, using real-time telemetry and automated guidance to neutralize incoming threats while aircraft operations continue uninterrupted on deck. At the electronic warfare level, the SLQ-32V6 suite monitors and disrupts enemy sensors, jamming communications, spoofing targeting systems, and creating openings for the ship to maneuver or launch countermeasures. Structurally, the Ford's hull is divided into over 2,000 watertight compartments, and critical systems are redundant and distributed. Even under catastrophic damage, flooding can be contained, power rerouted, and essential operations maintained long enough to recover or counterattack. The Gerald R. Ford class represents a pinnacle of naval engineering. Each ship costs approximately $13 billion, and with the full class of carriers planned, the total program exceeds $120 billion and is designed for a 50-year service life. Every system, compartment, and workflow reflects decades of engineering refinement, combining automation, human coordination, and survivability into one operational unit. For engineers, enthusiasts, and innovators, the Ford class is not just a ship. It is a moving laboratory of technology and design principles that will influence naval architecture for generations. To explore more engineering marvels like this, subscribe to Corecraft Engineering, where we break down the mechanics, technology, and ingenuity behind the world's greatest inventions.